Alright, so we're back. This is going to be a video about concavity and how it's related to inflection points. Now basically what concavity is, you can either have a function that is concave upward or concave downward, as I have with this blue and this red functions on this interval right here. Now this blue, within this interval, it is concave upward, and as you can see, the f prime of x is increasing throughout. So the tangent line at this point, all the way on, is increasing each point. Here it's about 0, but as you can see, it's increasing throughout this entire interval. The opposite is true for concave downward. F prime of x is decreasing throughout each point. As you can see, the tangent line gets smaller and smaller throughout, so that would be concave downward. Now, an important principle of this is that if f prime of x is increasing, as it is with this concave upward, then f double prime, or the second derivative of the function, is greater than 0. Okay, because the change is constantly increasing. That means the derivative, which represents the rate of change, is greater than 0 because it's increasing, it's positive, it's greater than 0. That's concave upward. The opposite is true for concave downward. If it's decreasing, if the derivative is decreasing, that means the f double prime, the second derivative, is negative, and that would be concave downward. Now, both of these examples show the concavity staying the same throughout. This is concave upward throughout the entire function on this interval, and then the same is true for this concave downward, only it's the opposite because it's down. But there are certain graphs where it'll be concave downward, and then it'll loop back up to be concave upward. Those points where the concavity changes is called inflection points, or points of inflection. And possible inflection points occur at points at which the second derivative is equal to 0, or the second derivative does not exist. So it's similar to when we use the critical numbers to test whether a relative extrema is a relative min or relative max, or neither. The same is true for inflection points. You can find these critical numbers of the second derivative where the second derivative is equal to 0 or does not exist, and they also have to be tested. So IPs, inflection points, must be tested just like the relative extrema has to be tested. I have an original function I just made up. It's just x to the third minus 3x. G of x is going to represent the first derivative, while h of x is going to represent the second derivative of this original function right here. So the first one, the only one I have turned on right now, is this first one, the x to the third minus 3x as such. So what I'm going to do is I can use this graphing utility, and if I click on the actual function, it will highlight certain points of interest. In this case, this relative max, this 0 point right here, and then the relative min. Now what I'm going to do for these points is show how they're related to this first derivative right here, this 3x squared minus 3. So what I'm going to do is I'm going to turn this graph on. Now as you can see, when I turn this on, this green function comes here, and this is going to represent the first derivative. And as you can see, this relative max that I have right here is equal to when the first derivative is equal to 0. So that x point is the same, so the negative 1 and negative 1 are the same for when this first derivative is equal to 0. This would be a critical number, and as you can see from the graph, it represents a relative max. The same thing happens over here with this relative min. So I have a 1 and a 1, it's equal to 0 for the first derivative. That's what this green is, the original function. That would represent a relative min for this case. Okay, this 0, 0 point is going to represent our inflection point where this whole graph changes from concave down to concave up. So since this is our inflection point, it should represent a point in which the first derivative is not changing. And at this point, it should have a horizontal tangent line. So that's how you can relate the first derivative with the original function to show where there's relative mins, inflection points, and relative maxes for these two. Also, a great thing that it shows is this first part right here, this x is less than 0, is concave down. As you can see, the first derivative is decreasing, 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 decreasing to represent where the first function, the original function, is concave down. All of a sudden it hits 0 right here, and then it starts to increase. As you can see, once it starts increasing, the original function becomes concave up. Another thing you can do if I turn this first derivative off and turn the second derivative on is the second derivative will show you where it's concave up and concave down based on the sign of the second derivative. So if the second derivative is less than 0, or if it's negative as it is right here, it shows that the original function is concave down. Now, when the second derivative is equal to 0, that shows where the inflection point is. So right here, it's at 0. It's changing from concave down to concave up. Also, as you can see, it becomes positive here. The second derivative becomes positive. As the second derivative becomes positive, then the original function becomes concave up. So that's basically, this example is just trying to show you how the first and second derivative are related to the inflection points and concavity of that original function. So if you have any questions about anything in this video, let me know.